Let's talk about resonance. Now, resonance is important when you start writing reaction mechanisms, and so you know about redistribution of electrons, etc. Also, you need to know, for example, when you see the Lewis dot structure in a textbook for, let's say, the molecule below CO3 2 minus, your carbonate ion, the overall Lewis structure that you will see in your textbook came from contributing structures. Those contributing structures are actually resonance forms. Contributing structures, same thing as resonance forms. Now, to draw resonance form for any particular molecule, what you're doing, you're basically showing the redistribution of electrons by using an arrow. And there's some little rules you have to follow as it relates to the movement of the electrons. Generally, you separate your resonance forms using a double-headed arrow. A single-headed arrow is used to show the movement of two electrons, right? So you can, there's some allowed distributions, right? So you're allowed to move a lone pair of electrons or redistribute it on an adjacent atom, on an atom, sorry, to an adjacent bond. So this arrow basically means that I have now moved these two electrons from here onto this bond, right? But here's the next rule. If I move these two electrons into this bond, right, we can't create a smiley face. We don't do that in chemistry. You actually have to write a bond. So the structure that you will draw over here is as a result of what the arrow here means, right? So like I said, and this is one allowed redistribution, right? You can go from a lone pair on an atom to an adjacent bond. Let me show you what that results in. So let's draw this carbon back. Please put back these lone pairs right here. The lone pairs right here, you need to put them back because I didn't redistribute them, right? So let's put them back. You need to put this lone pair and this lone pair back. Let's do that right now. Draw your oxygen. Atoms don't move, by the way, when you do resonance. It's just redistributing electrons, right? Now, remember, these two electrons, I have moved them here, but I can't draw a smiley face, right? So the two electrons become a bond. We're taking this step by step. Two electrons become a bond. Now, if the two electrons here become a bond, right? Look at this. This oxygen right here has two bonds to it, right? So guess what happens? Another rule is each atom must maintain its octet, right? So when I make this new bond with this oxygen, right, this carbon will have too much bonds on it, so I have to break one. Let's look, because here it is, 1, 2, 3, 4, 5. Can't have 5 bonds, so this is what happens. As these electrons are moving in here to this bond, the pi bond, one of these electrons, one of these bonds are moving onto the adjacent oxygen. It wouldn't make sense to move it onto the carbon. The carbon already, from what we see over here, has 5 bonds, right? So you move this arrow that I just drew means that the two electrons that is in this bond now goes on the oxygen. You don't put the bond on the oxygen. When you put it on here, when you put the bond on the oxygen, it looks like lone pair. So instead of having 4 lone pair, we now have 6 because I just put the 2 electrons from here onto the oxygen. So this is what I'm saying. If I move a lone pair, right, onto a bond, for example, you can't make a smiley face. We don't do that. It makes this. And if I have an atom, we have bonds, and I move the bond here, you can't draw this with the bond on it like that. Nope. The bond becomes lone pairs. Now, this is where what I taught you earlier comes in handy. Remember I told you to remember when an oxygen, a hydrogen, a carbon, and your halogens are neutral? It's important right here. If you take a look at this oxygen right here, it has two single bonds and two lone pairs, so there's no charge on it, right? Those are the things I told you to remember. Let's take a look at this oxygen. This oxygen has two, four, six lone pairs and one bond, right? This one clearly has a charge on it, and if you look on it, you'll carefully see that this oxygen would be more negative than a neutral oxygen, for example, in water. It has more lone pair, which means that these electrons are not being shared. They're all on the oxygen by themselves instead of being shared with an atom. So clearly that's more negativity, right? So that's a minus charge. We didn't do anything to this oxygen. Please realize I didn't touch this. So that's why it's back there, um, just as it was here. Something else to remember in resonance. If you have two charges over here, your next resonance form must have two minus charges. If it was neutral when we start, it needs to be neutral when you draw the other form. We can draw another form, resonance form here. So the electron, because there's nowhere else you can go to move to move electrons. I moved from here into here. Sorry, I moved from here into here and from here onto here, right? So the only next place or the next atom that we haven't given any attention is this one. So you go to this oxygen, you're doing the same thing. The lone pair can only move in here, right? And if I'm giving this carbon another bond, I have to remove one by putting the lone pairs on here. So draw the carbon. This oxygen up here will have a double bond because we did move those lone pairs. Don't know why I'm putting them back, right? We had moved them here into the bond. So we have a double bond here and we still have four electrons on this oxygen. Here, my double bond is broken and I now have, put back the two lone pairs, please. Put them back. We didn't do anything to them, so I put them back, right? Then this bond means that this arrow means that the two electrons in this bond is now on this oxygen. And let's put back the oxygen that I have over here. We didn't mess with it, put it back just as it is. To make this arrow a little bit smaller, I need some space. So oxygen and put back. That's a minus charge, this is a minus charge. Notice, one of the rules is you cannot overfill an octet, right? Can't have more than 8 valence electrons. That's why I had to move this out, right? You can't have more than that. And if you notice, I still have my 2 minus charges on that. And that's it for resonance. Just remember, you can move a lone pair of electrons. This is allowed from an atom onto an adjacent bond, and you can move 2 electrons from a bond onto an adjacent atom. You have to pay attention to what makes sense. If I'm putting a bond here, it's going to be on the carbon and it's going to be 5, so I need to remove 1. You couldn't move this one because you couldn't move this. If you move this, you're breaking up the molecule. You can't break up the molecule. The molecule stays intact. The only thing that you're redistributing, you can only redistribute lone pairs. You can only redistribute lone pairs and pi bonds whenever you're doing your resonance structures. And that's that for resonance structures.